In this video, we're going to present a proof of a fascinating conclusion. Some languages are not Turing recognizable. We've talked about decidable languages. We've talked about languages that are Turing recognizable. It turns out that there are languages that exist that are not even Turing recognizable. And in this video, we'll show the proof of why we know they exist. In the last video, we talked about the different kinds of infinity, countably infinite and uncountably infinite. The number of Turing machines is countably infinite. And we can show that by just stating that we can enumerate the set of all Turing machines. In other words, we can create a list of all Turing machines. There is an algorithm to start producing Turing machines, one after the other, such that we will list every Turing machine that can conceivably exist. How can we do this? Well, there are a couple different approaches, and both are equally valid. But we can encode a Turing machine into a string, and the strings have finite length. And we might even encode them into a string of ones and zeros. Every string of ones and zeros, then, is either a valid representation of a Turing machine or it's just random garbage that makes no sense as a Turing machine. It's either a valid description of a Turing machine or it's incoherent and not a valid representation of a Turing machine. So one way to enumerate every Turing machine is to just enumerate every string of ones and zeros. And we can generate all those strings one after the other. There are countably infinitely many of these strings, but we can enumerate all the strings of ones and zeros, all the strings of finite length of ones and zeros, one after the other. And then for each one of them, we can check to see whether it represents a valid Turing machine or whether it's just an incomprehensible piece of garbage. And in that way, we will list every single Turing machine eventually. Another approach to seeing that the number of Turing machines is countably infinite is to do our enumeration a little bit more intelligently. Remember that a Turing machine is specified by I guess it was a sextuple with number of states and the tape alphabet and the input alphabet and the transition function and the initial starting state and the accept state and the reject state. And maybe it was 6, I can't quite remember. But in any case, we have all these pieces that describe a Turing machine, and each one of these is finite, a finite set. For example, the alphabet of input characters is finite. The tape alphabet is finite. The set of states is finite. Okay? The kinds of transitions that we might have are finite, right? Every transition is labeled with a symbol that is being looked at and a symbol that is being written over that symbol and an L or an R to indicate which direction we move. So we have finitely many symbols, we have a finite number of output symbols, and we have only 2 directions. So there are only so many different kinds of edges we can create. And we have a finite number of nodes in the finite state machine that controls our Turing machine. So there's only a finite number of directed graphs with I nodes, assuming that we have a set of states with size I. We only have I nodes to work with. There are only a finite number of directed graphs, and there are a finite number of ways to label each of these edges. And we could, in theory, just generate all possible Turing machines this way. First, we start with Turing machines that have only 1 state, and then we start with Turing machines that have only 2 states, and so on and so forth. And we can literally just generate each possible conceivable Turing machine, one after the other. In either case, we have a way to enumerate all the Turing machines, so the set of Turing machines is countably infinite. Next, let's look at languages. Next, I want to look at the number of infinite length strings over zeros and ones. And it turns out that set is uncountably infinite. In the past, we defined a string as a finite length sequence over the alphabet. So technically speaking, the way I've defined string so far would not include any string of infinite length. But now I want to enlarge my definition of strings to include infinite length strings of zeros and ones. So imagine an infinite sequence made up of just the two symbols 0 and 1. How many infinite length strings are there? Well, that's an uncountably infinite number. Okay? And we can prove that in a similar way to proving that there are an uncountably infinite number of irrational numbers. After all, you can consider an infinite length string of zeros and ones to be a fraction between, or a number between 0 and 1. If you have some string of zeros and ones, such as this, that's infinite, well, if we put a decimal point, or actually we should properly call this a binary point, this becomes a number, right? Just like you can specify decimal fractions like this, you can also do the same thing in binary. Okay? And so if we put a point there, a binary point or a decimal point, if you will, in front of it, we get a number that is between 0 and 1. Okay, so, and actually, I should comment that I said less than or equal to 1. A decimal number with all nines, like that, is actually equal to 1. Okay, so there are, for some rational numbers, there is actually 2 decimal representations. Anytime you have a sequence of all nines, you can change it to zeros and put a 1 there. Okay, so there are 2 representations in decimal for a few rational numbers, those that end with a sequence of nines. So in analogy, when we're looking at binary numbers, if we have a binary number that is all ones, that would be equal to 1.0. Okay, that said, we're looking at infinite strings of binary numbers, and there are an infinite number of these, and it's an uncountably infinite number of infinite length strings of zeros and ones. And here's the proof, and it is basically the same as we saw with irrational decimal numbers. It's a proof by contradiction. Assume the set of infinite binary strings can be enumerated. Okay, so we can assume that we could list out every infinite length binary string in a table, and there would be a correspondence. One number is listed first, 1 is second, and another number is third, and then we have 4, 5, 6 numbers. So we can order these things if they are countably infinite. And then we can run down the diagonal, and we can create a new number that's different from all of those, or I should say a new string that's different, by flipping the bit. If it's a 0, turn it into a 1. If it's a 1, turn it into a 0. 1, 1, 1 becomes 0, 0, 0. And so we create a new binary string that's infinite in length, but that differs from every infinite length binary string in the table. So that proves that this table, that there's a contradiction. So we can't build the table in the first place, so our assumption that the set is countably infinite is incorrect by contradiction. And so the set of infinite length strings over zeros and ones is uncountably infinite. Okay, now let's talk about languages, and this is where it gets interesting. All right, let's restrict ourselves to an alphabet with only 2 symbols, and we'll use A and B as our symbols in the alphabet. And let's consider strings over that alphabet. So we could have, and here we're talking about normal strings, so each string has a finite length. This string, for example, has 3 symbols in it. And so here's a list of all the strings over A and B. The empty string, the strings with only one symbol in them. Then we have the strings with length 2, and then the strings with length 3, and so on. Okay? This is obviously an infinite set, but it's a countably infinite set because we can order them. Okay? We can list all strings of length 2 before strings of length 3 or greater, and then we can alphabetize them within that. Okay? And so this is a systematic way of listing all the strings, so we can make a correspondence with the natural numbers. So this is a countably infinite set of strings, of finite length strings. Each string is finite in length. For example, this one has 3 characters. There are an infinite number of such strings, but that number is countably infinite. Now, let's talk about a language. A language contains some of those strings and not others. So here I'm making up a language. It's an arbitrary language, and what I'm doing is I'm circling the strings that are in the language and not circling the other strings. So this language consists of the empty string B, AB, BB, AAA, but not strings like BA or AAB. Okay, so a language is a subset of this countably infinite set of strings. Okay, it contains some of these strings, but not others. Now, we can specify a language with an infinite length binary string. Okay, the set of all possible strings of A's and B's is infinite. Okay, so imagine an infinite binary string, and we put a 1 wherever that string is in the language, a 0 wherever that string is not in the language. So for my language that I've got here, the binary string that describes it starts off 1, 0, 1, 1, 0, 0, 1, 1, 0, and it's an infinite length string. So it's an infinite length binary string. Every language can be fully, totally, completely specified by giving an infinite length binary string. Okay, or at least over an alphabet with only 2 symbols in it, like we're talking about here. Okay? Now, how many infinite length binary strings are there? There are uncountably many infinite length binary strings. Therefore, the number of languages is uncountably infinite. The number of languages is uncountably infinite. So let's go back to our previous result. We said that the set of all Turing machines is countably infinite. So what that means is the set of all Turing recognizable languages is countably infinite. For every Turing recognizable language, there has to be a Turing machine that can recognize it, because that is essentially the definition of what it means to be a Turing recognizable language. So therefore, since there are only countably infinite many Turing machines, there are only countably infinitely many Turing recognizable languages. But we just showed that the set of all languages is uncountably infinite. So the remarkable conclusion is that some languages are not Turing recognizable, that these languages that are not Turing recognizable do exist. And in fact, because we know what we know about countable and uncountably infinite, a whole lot of the languages, I guess you might say the vast majority of the languages, are not Turing recognizable. Although I hesitate to make comparisons like that when dealing with quantities like uncountably infinite. I think it suffices to say that there are languages that are not Turing recognizable, and there's an uncountably infinite number of them, which is a lot.